Welcome, Recruit. Today's explainer is your official, highly classified tactical briefing. Your mission, should you choose to accept it, is extracting absolute maximum marks from the Cambridge Computer Science syllabus. We are primarily targeting 9618 today, but listen, whether you're looking at syllabus codes 0417, 0478, 0983, 0984, or even 2210, the extraction strategies we are going to deploy here are absolutely universal. Picture this. You are a secret agent. You are sitting in that exam hall. The clock is ticking down. You've got maybe 20 minutes left to secure a massive chunk of your grade on a hostile, incredibly complex past paper question. We aren't just looking at how to memorize code today. We are looking at the metagame of the exam itself. How do you extract the marks when the pressure is on? Let's get started. We are dropping right into a notorious minefield in the exam paper. Look at this direct intel straight from a senior examiner. They are making it abundantly clear that the key features of stacks, queues, and linked lists are brutally misunderstood. These structures form the absolute backbone of dynamic data processing, yet year after year, candidates walk right into traps and leave massive amounts of marks on the table. Why? Because they understand the concepts in isolation. But here's the secret. The exam paper isn't about isolation. It is a hostile environment. It is about application under intense pressure. We are going to completely fix that disconnect right now. All right, here are your mission objectives. 1. We'll establish our core intel on theoretical architecture. 2. We'll break down the exact extraction procedure. 3. We'll run a threat assessment on examiner warnings. 4. We'll deploy the method mark strategy. And 5. We'll lock down the evaluative tactics to secure those top-tier grades. Okay, let's dive into our first objective. We need to establish the foundational principles you're going to deploy out there. Consider this your core intelligence briefing. Here's the truth about top-performing agents. They do not just sit there and memorize definitions. It is simply not enough to walk into the hall knowing that a stack operates on a last-in, first-out, or LIFO basis, or that a queue operates on a first-in, first-out FIFO basis. The Cambridge syllabus explicitly demands that you master 3 distinct cognitive domains: knowledge, application, and analysis. You absolutely must be able to transfer your cross-topic connections into entirely unfamiliar, sometimes frankly bizarre contexts to secure higher marks. Think about it. When the exam throws a wild scenario at you about a network printer spooler sequentially processing hundreds of print jobs from different departments, you need to instantly identify that architecture as a queue. Boom. Application. When it asks about a web browser's back button navigating your recent history, you must immediately establish the causal relationship between that real-world problem and the underlying theoretical architecture of a stack. That is how you level up. So, knowing the theory is really just step 1. Let's move to our second objective and see how the tactical methodology builds to actually extract those marks. When you open the paper, the clock is ticking, your adrenaline is pumping, and you encounter a complex data structure problem disguised as a scenario you've literally never seen before. What is your immediate first move? Do you just start writing pseudocode and hope for the best? Do you panic? Absolutely not. You take a breath and you initiate the extraction procedure. This involves what we call the PEEL framework: point, evidence, explanation, link, and rigorously decoding the specific command words Cambridge uses. Before we continue, subscribe to our YouTube channel Ace the Exams at aceexams_GICSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. You must deploy this precise 4-step procedural framework every single time. First, deconstruct the question. You have to hunt down those command words. Are they asking you to simply describe the structure? Or are they asking you to explain its function in context? Or maybe evaluate its efficiency? These command words dictate the exact depth of your answer. Second, extract the relevant data. Pull the specific constraints, the data types, and the limitations right out of the scenario's text. Third, select your analytical framework. This is where you decide, right in the moment, if a linked list's dynamic memory allocation is better than a static array for this specific problem, usually because the data volume is completely unpredictable. And finally, step 4, execute with clear notation. Ensure you use the correct terminology before writing a single line of algorithmic code. You map it out first. Now, to lock down this step-by-step algorithmic decomposition under intense exam pressure, you need to use a visual story method. This securely encodes these complex data structure concepts in your memory so you don't blank out. For a stack, imagine a literal physical stack of heavy ceramic plates at a cafeteria. You can only take the top one off, right? If you try to pull from the bottom, the whole thing crashes. That's LIFO. For a queue, think of a frustratingly slow line at a theme park on a hot day. The first person who got in that line is the first one getting on the roller coaster. That's FIFO. Visualizing the actual flow of data prevents panic. It gives you a concrete mental model to rely on when the exam scenario gets complicated and tries to confuse you. Now, let's transition to Objective 3 and assess the traps that take out most candidates. This intel comes straight from the principal examiner reports. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's assess these 3 critical threats. Threat number 1, providing vague answers. Examiners absolutely hate it when you just write, "The pointers change." Which pointers? From where to where? You must specify if it's the null pointer, the head pointer, or the next node pointer. Threat number 2, ignoring vital boundary conditions. If you don't check if a queue is empty before trying to dequeue an item, your algorithm crashes and so does your grade. And threat number 3, the biggest one, completely failing to apply your knowledge to the given context. If the question is about an automated airport luggage routing system and you write a generic, memorized textbook answer about integers in a 1D array, you will lose the application marks completely. This brilliantly illustrates the exact difference between a failing strategy and a winning one. Let's look at 2 candidates. We have Alex on the left. Alex panics and overloads the answer with raw computer science facts, literally dumping everything they've ever memorized about linked lists onto the page, but totally ignoring the actual question's constraints and canard words. It's just a wall of text. 0 application marks. Now, contrast this with Sam's approach on the right. Sam takes a breath and uses a precise, context-driven extraction. Sam uses the Peel framework. Sam makes a point, backs it up with evidence from the prompt, explains how the technical details of nodes and pointers directly apply to the scenario provided, and links it back to the command word. Sam gets the marks every single time. Don't be like Alex. Be precise, be contextual, be like Sam. So, the crucial point we are moving to next is Objective 4. This is your tactical safety net, known as the method mark strategy. Listen to me carefully here. The examiners are explicitly alerting you to this fact. You must always document your systematic step-by-step working. Why? Because the process itself guarantees marks even if the final code fails to execute perfectly. Let's say you are writing an algorithm to push a new item onto a stack. You correctly implement the if statement to check for overflow. You correctly increment the top of stack pointer, but in the rush of the moment, you accidentally assign the data to the wrong index variable at the very end. Your final answer? Technically wrong. It won't compile. But because you showed the logic of checking the boundary condition and moving the pointer first, the examiner awards you the vast majority of the method marks. Show you're working always. Do not do it all in your head. For our final mission objective, we elevate our strategy. We are moving into the deconstruct, solve, evaluate loop required to achieve top-tier critical analysis. This is where you separate yourself from the average candidate and secure the highest grades. When you are hit with an evaluate command word, it is absolutely crucial to rigorously analyze trade-offs. Top-scoring candidates don't just pick a data structure and walk away, they critically evaluate it against the alternatives. You need to analyze the time complexity. For instance, you need to articulate how slow it is to traverse a linked list sequentially, node by node, compared to the blazing speed of jumping directly to an index in a static array. You need to analyze the space complexity. Are you wasting precious memory allocating a massive contiguous array for a queue when a dynamic linked list would only use the exact memory it needs at that exact moment? You must demonstrate this evaluative thinking by weighing these trade-offs directly against the specific constraints of the exam question. It only takes one unacknowledged boundary condition or edge case to ruin an algorithm's performance. Think about it, just one. Attempting to pop an item off a stack that is already empty results in a fatal stack underflow. Attempting to insert an item into a queue that is already at maximum capacity causes an overflow error. And if you are dealing with a circular queue, a very common high-mark question, failing to properly calculate and wrap that rear pointer back to the start of the array will break your entire program instantly. Checking for reasonableness and accounting for that single critical edge case in your pseudocode is absolutely non-negotiable if you want full marks. So apply this 4-step evaluative sequence to thoroughly test your implemented solutions. Step 1, break the problem into logical steps. Step 2, consider multiple solutions. Could this specific buffering problem be solved more efficiently with a circular queue instead of a standard linear one? Step 3, acknowledge the limitations of your chosen method. And step 4, make evidence-justified recommendations, backing up your final decisions with hard data from the prompt. This is the blueprint for a perfect evaluative answer.
And look, students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by.
As you finalize your preparation for these crucial Cambridge exams, ask yourself, are you just blindly memorizing facts, or are you ready to critically evaluate the edge cases of every system you build? Your extraction methodology is now complete. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Good luck on your mission. Dismissed, Agent.